we are still into the introduction to integral calculus. Last time I spoke about integral calculus as obtaining the area of a plane region. That is one way to look at integral calculus. But there is another way to look at integral calculus, and that is integral calculus as the antiderivative or anti-differentiation. Integration is the reverse process of differentiation. It's the reverse process of getting the derivative. That's why you call it anti-differentiation. So what integral does, what it does is it undoes differentiation. It undoes what the derivative is doing to the function. So the connection between the integral and the derivative is embodied in a theorem. We call that in math as the fundamental theorem of calculus. It's like anyone who is studying calculus must know this. This is the relationship between integration and differentiation. So this is how we can look at integration and getting the derivative. Suppose I have a function defined by f of x plus c. Okay, c is a constant. And what I'm going to do is I will put this on a conveyor belt that will bring it inside a machine. Okay, and this process, okay, what the machine is supposed to do is to give the derivative of f of x plus c. And you know how it's done, okay? So our symbol for that is this one. F prime of x is equal to a function. Okay, let us call that small f of x. Where is c here? What happened to c? Well, the derivative of a constant is 0. That's why the derivative of f of x plus c is just equal to f prime of x. And so this one is another function. Now, this is what we will do. We will bring back this derivative, okay? Small f of x is the derivative of big f of x. What I'm going to do is I will return this back into the conveyor belt so that it will enter the machine. And what will come out from that machine is this one, the original function, capital F of x. So you can look at this process, okay? Big F of x enters the machine. What comes out is the derivative. So that process is about getting the derivative of a function. But when you return this back into this machine, okay, what it does is it performs integration. It gets what is the integral of this function. But this function is the derivative of your original function, capital F of x. And so when you bring this back into the machine, it will send you back to the original function, capital F of x. And so this relationship is embodied in this theorem. We call this the fundamental theorem of calculus. If a function f, okay, big F, is called the antiderivative of small f in the interval, closed interval a and b, if the derivative of big F of x with respect to x, so this is our one notation. We have many notations for getting the derivative, but this is one. The derivative of big F of x with respect to x is equal to small f of x. What this means is this one, f prime of x, is equal to the small f of x for all x in the interval. Okay? Now, this is how we say it, okay? The general antiderivative of f of x. Okay, again, integration as anti-differentiation. The general antiderivative of f of x, what you do here is you get the integral of f of x dx. And it will bring you back to the original function, capital F of x plus c. So this is what is embodied in the fundamental theorem of calculus. Example 2.1. Use the definition of antiderivative to show that this function, capital F of x is equal to 3x cubed, is an antiderivative, or is the antiderivative of small f of x, which is equal to 9x squared. Okay, so how do we do that? Okay, so we must show that when we obtain the integral of 9x squared, the antiderivative of 9x squared dx, that is the integral of 9x squared dx, is equal to 3x cubed. So why is that so? In fact, that is the antiderivative. Why is that so? Because when we obtain the derivative of 3x cubed plus c, look at this. Derivative of capital F of x with respect to x. If we were to get the derivative of this is going to be equal to 3 times 3, that's 9. You subtract 1, it becomes 3x squared. And then plus c. Use the definition of antiderivative to show that capital F of x, which is equal to 1 over 3 times e to the 3x, is the antiderivative of this function. So what do we do? This one, if I were to get the derivative of this with respect to x using your chain rule and power rule, the chain rule, this is basically the chain rule and the derivative of your natural exponential function. So the derivative of that is equal to 1/3 times e to the 3x times 3. So that is how you do chain rule. 3 divided by 3 is equal to 1, so you are left with e to the 3x. So what does that mean? It means that if you were now to get the integral of e to the 3x dx, get the integral, it will bring you back to this function. To this function, 1/3 times e to the 3x plus c. Use the definition of an antiderivative to show that ln of x is the antiderivative of 1 over x. Well, what do we know? The derivative of ln of x is 1 over x. And so if you were now to get the integral of 1 over x dx, it should bring you back to ln of x plus c. We always add c. So by the way, why do we always add c? So when you are obtaining the general antiderivative, that is what you call it, the general antiderivative, you always add c here. Why so? Because, look at this. If we shall get the derivative of this with respect to x, it's going to be, the derivative of this with respect to x is, 1/3 times e to the 3x times 3. 3 divided by 3 is 1. So you are left with e to the 3x. That's 1. But what is the derivative of a constant? It's 0. It's the same with this one. So what is the derivative of ln of x plus a constant? It's 1 over x plus 0, which is 1 over x. Which is why when you now get the integral of 1 over x dx, that should return you back to ln of x plus c. So remember that when you are obtaining the general antiderivative, you will always append plus c.